Welcome to my project bazaar.com. Here we are going to discuss about the pipelined Radix-25 feed powered FFT architecture. In this project mainly focus on the multiplication involves two basic operators, generator of partial product and accumulation of a partial product. Hence all techniques for speeding up multiplication can be categorized into two main groups. Those that seek to reduce the number of non-zero partial products and those that seek to accelerate the accumulation of partial products. The three main classes of multiplier include partial multipliers, many multipliers and iterative multiplier. Per multiplier generate partial product in parallel and accumulate them using a fast multiple operand order. With this type of multiplier design, the execution of speed is increased at the expense of the increasing area that is required for the generation of multiple partial product in parallel. Further speed up can be achieved by using an array multiplier, where an array by identical cells generates a new partial product and accumulates them simultaneously, such that separate circuits are not required for generation and accumulation. Array multipliers are used widely where high speed multiplication are required. However, in addition to recurring large area, array multipliers usually do not seek to optimize energy efficiency through exploration of the specific data dependent patterns of digits that occur in the multiplier and multiplicand. The typically array multipliers are in currently enhancement. These two considerations limit many practical application of both parallel and array multiplier. Typically, the shift at a functional block implemented in an iterative multiplier shift. The operand by a fixed number of bits and fixed number of iterations are required to produce the final product, which has side flowed approach. The control and strategicals. The new iterative multiplier structure proposed in this paper employs a variable of iteration to convert one operand from two convert to a canonical signed digits represented in a real time by using a new CSD recognition method where the number of iteration is data dependent. The novel real-time CSD recording is very simple implementation and records only a few combination logicals. In fact, the actual CSD representation of the multiplier operand is never explicitly present in the hardware. Rather, only the control signals that are required for a accumulation. The partial product based on the values of the multiplicand are generated by the exploiting the inherent properties of the CSD numbered system. The proportional multiplier increases the number of zero products and approximately by 60%. Each time a zero partial product occurs, the corresponding add operation is automatically node. Here we are going to discuss about the system flow diagram. In this flow diagram represents the flow of our process. First of all, we give the input to the input register. The input register is divided into the k number of point FFT. It's split into the multiple bits. These multiple bits are divided into the butterfly unit. This butterfly unit comply with the CSD multiplier. In case of the k point is controlled by the control unit. And the finally CSD multiplier, if condition satisfied, we pass into the output. If it didn't satisfy our condition, we go to the second iteration. In this condition rotated from the when the condition satisfied, close all kind of operations. This is our system flow diagram operations. Now we are going to discuss about running procedure of our project. In our project we have four steps. First step we check the syntax error, then second step we generate the RTL schematic diagram, then third step we generate the technology schematic diagram, then finally we generate the simulation waveform. First of all we select the implementation, then select main function and select check syntax. Now we are going to check the syntax error of our program in case of any warning and error that displayed in our console block. In our process we have no syntax error. Now we are going to the second step, select RTL schematic and run it. Now we are going to generate the RTL schematic diagram. In this step take few minutes. Then next we add, then select create schematic. This is our overall RTL schematic diagram. data in and clock. These two signals are our input signal, data out our output signals. This is our internal RTL schematic diagram. Now we are going to the third step. Select view technology schematic and run it. Add, create schematic. This is our overall RTL technology schematic diagram. Please wait. This is our internal block diagram. This internal technology schematic diagram consists of number of LUTs and flip-flops. This is our overview technology schematic diagram. Now we completed up to 3 steps. Now we are going to the final step. Please select simulation and select main function and select simulate behavior model and run it. This is our initial simulation waveform. Now we are going to give the initial input values. Give clock value to 0. Data in value set, give any random input and run our program. This is our initial conditional output. Now again we change the clock value set to 1 and run it. Then again change our input signals. And set the reset value to 0 and run our program. Then give the input values. Give the input value up to 32-bit. And run our program. Then I can change the clock pulse only. Then I can change the clock signals. Then I can change the clock signals. Then I can change the clock signals. Set to 1. This is our final output. Now we complete our running procedure. Thank you.